Hi everyone and welcome to this video. In this video, we are going to talk about a simpler picture of the origin of the band structure in solids. So if you have actually studied about the band structure in solids, or perhaps even maybe even come across in your elementary physics class, the word band structure or perhaps the word band gap of a semiconductor. So if you start um, reading about this, so the theory is fairly complicated. And if you start reading about it, first you have to learn about perhaps the Sommerfeld theory of metals or perhaps the Drude model. And then you get to crystal lattices and crystal structures and various types of unit cells. And then you get to Bravais lattices and then reciprocal lattices. And honestly, it's quite overwhelming. So I've decided to actually present a simpler picture of how the band structure of a solid, what is the origin of that. So I'm going to present a simpler picture here, and hopefully you are able to understand. So let's get started right away. So the picture that I have here on screen, this is called the chronic penny model. The chronic penny model, and maybe you might have studied this in your quantum mechanics course, but it's all right if you haven't, because I'm going to go through this anyway. So what we have here is you can think of a 1D arrangement of atoms. So evenly spaced atoms. There's one atom here, another atom here, another atom here, another one here, and so on. And this, we'll assume that this goes on till infinity. So we actually have an infinite uh, array of atoms in one dimension, mind it. Um, so, and these atoms, as you might know, these give rise to a potential because of the interaction between the atoms, because of their electrons and because of their nucleus. So we'll assume that the potential looks something like this. Now, this is a very simple picture. It's not actually like this, but we are going to assume. So actually, Kronig and Penny, they gave this simple picture. So we're going to assume that the potential actually looks like this. And so we'll assume, so every atom has electrons. So say there's an electron here, an electron here, and an electron here, and an electron here. So actually there might be more than one electron. And yeah, it's important to assume here that the electrons inside an atom, we are ignoring the interactions that they have with themselves. So we are just assuming that um, the electrons of different atoms, they will interact with each other, but the electrons inside the same atom will not interact with each other. So it's an important assumption. So let's say this level here, we will define it to be the zero potential, and this level here we'll define it to be U naught. And we'll call this separation B, this right here, and this one, we are going to call it A. And next, what we are going to define, we'll define A naught as A plus B. So this is just for some simplification, which we'll be using later. So A naught is defined as A plus B, and we will, let's say we will define our origin here. So this is x equals to 0. This is x equals to A. So this will be x equals to minus B. I want to remind you that this is a periodic structure. So this width is A and this length is B. And so this is also A, this is again B, this is A, and this is again B, and so on. This goes on till infinity. So next, what I want to do is I want to write the Schrodinger equation for this system. So what is the Schrodinger equation? So I'm going to assume that you are aware of basic quantum mechanics here. So I'm going to write the time independent Schrodinger equation. So this is the time independent Schrodinger equation, and if you have studied this, then it's good. If you haven't studied this, then I recommend you that you can go through some textbook. So there's a textbook called Introduction to Quantum Mechanics by David Griffiths and Daryl Schroeter. So I highly recommend this book. So it has much of the mathematical formalism that concerns the Schrodinger equation and how to solve basic quantum systems with the Schrodinger equation. So I recommend that you go through this book if you have never studied the Schrodinger equation before. So firstly, coming to the region that lies between 0 and A. I'm going to write the Schrodinger equation. So it will be, and I'm going to call the wave function psi as psi A in this region. And since the potential in this region is 0, so this term will be 0. So we are going to have just the energy term, and rearranging this, we are going to get, and I'm going to rewrite this as minus alpha square psi of A. And here alpha equals 2me for h bar square. And the solution will be of the form. Similarly, I'm going to talk about the region, which is this one. And again, I'm going to write the Schrodinger equation. And this time I'm going to refer to the wave function as psi b in this region. And so now we have this potential here, which is u naught. So we are going to have to write this term. So we are done writing the solution here. So next, what I'm going to do is I'm going to apply some boundary conditions on this. So the boundary conditions are that at the boundary, that is x equals 0, the wave function must be continuous, and the derivative of the wave function must also be continuous. So that basically translates to these two conditions. And now if I use these two conditions, what I'm going to get is this. This is from the first condition, that is psi of A at x equals 0 will equal psi of B at x equals 0. And the second condition will dictate that BA times alpha equals BB times beta. And for simplicity, just to get rid of the subscripts, I'm going to assume that this is equal to A. And I'm going to assume that BA is some B. Rewriting quickly, we get next what we are going to do is we are going to use something called periodicity. Well, it might be obvious, but we would have to use periodic boundary conditions. So what I'm going to say here is that psi of A equals, I'm going to explain what I have just written here, these two equations. So this equation states that psi of A at x equals A is directly related to psi of B at x equals minus B. And so is the case about their derivatives. So the derivative of psi at x equals A and the derivative of psi at x equals minus B, they're also directly related, which makes sense because if I look at this picture, this point at x equals A is basically in some way identical to this point because this is a periodic structure. So this repeats after every A plus B distance. But you may ask, what about this factor here, this exponential ik times A plus B? So you just have to believe me for now, but this comes from something known as the Bloch's theorem, and you might look it up on the internet for now, or perhaps I'll make a video about it later as well. But you just need to believe me for now. So this k is actually the wave vector, and uh, since we defined A plus B to be A naught, so I'm going to use this instead of writing A plus B every time. I'm just going to use A naught uh, uh, from now onwards. So what we now get after using these two uh, boundary conditions. So I'll just write it out. So from the first boundary condition, we get, now what I'm going to do is, so what we basically want at this point is we want to eliminate A and B because, I mean, uppercase A and uppercase B, because we don't know what A and B are. So we just want to eliminate them. So what I'm going to do is I'm going to rearrange this and write it so that we have A and B on the same side, the the coefficients of A and B on the same side. So now I'm going to write these equations in matrix form, and you'll shortly get to know why. So I'll just quickly write it. That's it. I'm done writing the matrix here. So we now want to eliminate A and B. So if you look at this matrix equation, you might be able to identify that this is just an eigenvalue problem. So the thing here is we have an eigenvalue equation, but the eigenvalues are equal to 0. That means that this matrix right here, this square matrix which I have, its determinant must be equal to 0 because we have eigenvalues that are equal to 0. So I'm going to use this fact to now write another the determinant of this matrix, and you will see shortly what we'll get. So let me just write this down quickly. So now we have these equations, this equation here, and I've actually simplified uh, this term, and written it in yellow here. So I'm going to rewrite this equation. Now going to divide. So first of all, I'm going to cancel this factor, uh, and I'm going to divide this equation by the term 2 alpha, and I'm going to rearrange this equation and rewrite it in another form, which will be useful. So hang in there with me. So we have arrived at this equation, and this equation is quite important for what we are going to do next. So now I want you to recall how we defined alpha, the parameters alpha and beta. So if you recall, I had defined alpha to be equal to under root 2m e over h bar square, and similarly beta. Now two cases arise. So it is a general system. So the energy E can be both greater than U naught, or it can be less than U naught. So it can be anything. So now I'm going to define two cases. One in which the energy E is less than U naught, and the other one where it will be greater than U naught. And then we'll rewrite this equation which we have in this box. We're going to rewrite this in for both the two cases, but I'm afraid I have to, for the sake of brevity, I'm not going to write the entire calculation. I'm just going to write the expression. So I I ask you to do this simplification yourself, and this way you'll get to you'll get used to this manipulating heavy equations yourself. So I urge you that you do this uh, manipulation and this rewriting yourself. I'm just going to write the equation right away. So case one, I'm going to define E over U naught as some epsilon, and this will be less than 1, which implies that energy is less than U naught. So this equation in this box, this will get simplified too. So I must define this alpha naught here. This is equal to this quantity. And I've actually defined this here for convenience. Similarly, now I'm going to write case 2. So I have written down uh, the equation for the two cases, and now we are going to plot this equation. So the way that we are going to plot this, and you will understand why I have defined this epsilon here. So the way that we are going to plot this is this. I'm going to plot for the above two equations. I'm going to have the quantity epsilon, that is E over U naught on the x-axis, and I'm going to have the left-hand side of these equations on the y-axis. And there's one other thing which I want you to notice, and this is very important. So notice that the right-hand side of these two equations, we have the term cosine of k times a naught. Uh, So, and if you observe, so cosine of k times a naught, this can take values only between 1 and -1. Now this fact is quite important. So I'm just going to mark 1 and -1 here. So first I'm going to plot the above equation that is in blue. So for epsilon less than 1, so I'm going to mark 1. And if you use any standard plotting software, let's say Desmos or whatever you prefer, if you plot an equation like this, and you can actually try this, um, if you plot this equation, I'm sorry, there's a slight uh, mistake from my end here. There's an under root here. So as I was saying, if you plot this the left hand side of this equation, you can just instead of alpha naught and a, you can, and alpha naught and b, you can just plug in any values, let's say 5 or 4 or 10 or whatever. And if you actually plot this, you're going to get something like this. So this graph actually comes down from infinity, and it ends up something like this. And for epsilon greater than 1, if you plot the graph, so looking at this expression, you might think that this is a periodic function, but it is actually not. And this isn't very obvious. Like you might intuitively feel that this is not a periodic expression, but yeah, I'm not going to prove it here. But this turns out to be not periodic, and it looks something like this. And as you move, so as epsilon increases, the separation between these waves, it actually increases, keeps on increasing. I'm not able to depict that very clearly here, but again, if you do it on a plotter, then I think it will be much clearer. So next, what we are going to do. So I want you to consider this region. So remember that for us to have a solution, the the solution should lie between -1 and 1. That is because the right hand side of these two equations, right, it's a cosine, so it has to be between -1 and 1, which means that this solution which lies outside, that is greater than 1 and less than -1, these regions are automatically rejected. So the valid solutions which we have here, so I'm going to point out the the regions where we will have a solution, and that is this box right here, and again this thin box right here, and again I'm going to change to a different color, and again it will be this one right here, and again this one, And so this actually goes on. So there are going to be an infinite number of solutions, but the main point here is the solution space. It's not going to be continuous. So what this implies is that there are some there is some range there are some ranges of energies where there exists no solution. So for example, this gap right here, this range of energy, there would be no solution. Again, this range of energy, no solution. No solution for this range and this range and this range. So this is the important point. So there, so what I'm trying to say that there are only certain bands of energies that are allowed. So another way to represent this would be in terms of an E versus K diagram. So what we are going to do is we are going to make a plot of the energy versus K, the same parameter K which we have defined up there. So this is K. This will be pi over A naught. This will be minus pi over A naught. Now I want you to observe that at K equals 0, cosine of K times A naught is actually equal to 1. So let's just consider what I'm going to do. I'm going to consider these two ranges of solution, this one and the other one, this one. So at K equals to 0, which is at the center of this graph, this is K equals to 0. So at K equals to 0, this so cosine will equal 1. So it's actually this energy. And as K goes from 0 to pi over A naught, so cosine of pi is minus 1. So this actually moves from this point to this point. So the energy actually decreases as we go from uh, K equals to 0 to K equals pi over A naught. So the way that I can represent this is, and yeah, we have energy on the y-axis. So the way that I can represent this is, so let's say there's a dotted line here, there's a dotted line here. So at K equals to 0, there's a high energy, and as we move from here, the energy decreases. So I can actually represent this as in this way. And similarly, if you move from K equals to 0 to K equals minus pi over A naught, and I want to remind you that this is a periodic structure. So this will actually repeat after 2 pi over A naught. So the mirror image of this happens here. And similarly, the band which is just above this, that is in red. So the same thing happens at K equals to 0. Uh, the energy is actually low this time, and as K goes from 0 to pi over A naught, that is cosine equals minus 1, the energy increases. So this will look something like this. Same on the negative side. So I pardon me for my drawing, but so this will be a mirror image around the y-axis. So this is, so you might have actually come across this picture because this is a very popular picture. So this region, which is in between these two, there are no allowed energies here. So this is actually the band gap, and which is also commonly called the band gap, the semiconductor. So now I have presented you with um, a very easy to easy to understand image of how these band gaps come about. So the next thing what I want to do is um, I want to I want you to intuitively understand what it means for if we let's say let's go back to the chronic penny model picture. So what if you remember what I drew was this. So what does it mean for atoms to exist individually or uh, and on the other hand for them to exist in a crystal? So let's say so this potential, the height of the barrier here is u naught and b is the separation. So what does it mean for an electron to have this band of energies, this allowed range of energies? What I'm going to do now, so I'm just going to redraw the graph which we had up there. I'm going to draw a quicker and simpler picture to make my point. So we had the graph coming like this, and we had an allowed band of energies here. Let's call this energy here as E1, and this energy here, I'm going to call it E2. So my question is, what happens to the separation between E2 and E1, that is E2 minus E1, as B, that is the separation between atoms, as B is increased? I want you to think about it for a moment and come up with an answer, and let's see what you think. So I hope you have thought about it, and the answer is as B is increased. So we are pulling apart atoms far away from each other. So atoms will now try to act like they are independent of each other, and they'll try to influence each other less because we are increasing the separation between them. So what really happens to the energy of these electrons? So if we have guessed it right, so if the separation is less, so this curve, which is coming right, so if the separation is less, this curve will have the magnitude of the slope will be much less. So let's say E1, this is E1 and this is E2. But as the separation is increased, so we increase the separation, now the curve will come much more steeply. So this is E1 now, and this is E2 now when the separation is increased. So with increase of separation, it is as if this range of energies that was earlier allowed, this has reduced. So as we keep increasing the separation between atoms, this E2 and E1, it will eventually coincide. So this will tend to zero. And this actually makes sense. So as if we look at an individual atom and we ask what is the energy of electrons in that atom, so we have this Bohr picture of the atom, or let's say the Schrodinger's picture of the atom, and what they say is that the energy of electrons is discretized. So uh, so the energy is discretized, and we are talking about separation increased to a much greater value. So what will happen now is this curve will go something, will almost be vertical. So the energy of electrons will now, instead of a range of energies, it will now just come down to a point. So this will be one allowed energy, this will be another allowed energy of the electron, another one here, another solution here. So we eventually come back to the single atom picture, how what will be the energy of an electron in a single atom. And that's what is happening here. As we are increasing the separation, the atoms are acting like as if they are independent of each other. One atom now has less influence on the other, and the same thing happens if we increase u naught. So if we were to increase this potential, a similar thing will happen, that is equivalent to if we increase the separation between atoms. So uh, let's say u naught is very large. So what will happen now is these atoms will again start behaving as if they are independent of each other, and because of this large potential barrier, uh, this electron will be unaware of the existence of this atom, and it will be unaware of the existence of the electron here. So again, the same thing happens. Um, uh, the energy range, the allowed energy range, this will start shrinking again if U naught is increased. And we can also say another thing. So what we can say is that as atoms are brought closer to each other, this is the separation between atoms, and this is the energy. So what we can say is that uh, as the distance between atoms decreases, a single energy, so let's say this is a faraway separation, the atoms are far away, a single energy begins to split into two energy levels as atoms are brought closer. And let's say this will be equal to E2, this will be equal to E1. And we can actually extend this simple picture to, let's say, now consider the case of molecular solids or perhaps organic compounds. Why do these materials not have a well-defined band structure? So if you think about it, um, a well-defined band structure in comparison to, let's say, metals or semiconductors. So if you think about it, these molecular solids or organic compounds, they have very weak interatomic forces, or even very weak intermolecular um, forces at play. So with very weak interactions, as I just said, and because of the increased interatomic distance and also very weak interactions between their atoms and their molecules, uh, these uh, materials behave, there's no formation of a band in the first place because of the large separation. So we don't have such a well-defined band structure in this case, and this is the reason why these materials don't have such a well-defined band structure, because that can be explained in this picture that I just presented here. So the separation is large, or perhaps the barrier between atoms is very large. So we can say, we can explain this behavior of molecular solids or organic compounds through this picture. So I hope you have watched this video till the end, and I know because this video had a lot of mathematical formalism and a lot of equations, and I hope you did not get lost in the maths. But I urge you to go through the video again if you have not understood some point, and let me know in the comments below if I can answer any question for you. And I urge you that you go through the video if you have not understood some point. The maths may look overwhelming or perhaps complicated, but it's just if you do it step by step, you're guaranteed to arrive at the equations. And let me know if you like this video by leaving a thumbs up. And if you did not like this video, then please let me know in the comments, and I'll be happy to look at some suggestions on how I can improve. And if you have more ideas on what topics I should make videos about in the future, then please let me know in the comments as well. And thank you very much for watching.